Hello, everyone, and welcome back to this last tutorial session of the day, focused on RL. So this, as in the morning, this will be a 2-hour session. There will be a very short break in the middle for a few questions, and there will be more time for questions at the end of the session. So now it's really my great pleasure to introduce the speaker of this session, Katja Hofmann. Apologies, there's just a small mistake in the printed program in her affiliation, so she's not anymore affiliated with the University of Amsterdam. She did her PhD there, but currently she is a principal researcher at Microsoft Research in Cambridge, UK. Katja has made a lot of contributions in the field of RL, and I would just like to highlight one of them that I'm sure you're familiar with, and that is Project Malmo, which uses Minecraft to provide a platform for experimentation in RL. And I think this sets such a great example for how we can facilitate access to resources in research that can really accelerate progress in the field. So please join me in welcoming Katja.
Thank you so much, Viorica, for the kind introduction. And thank you so much for being here today. I'm really excited to be able to talk about why reinforcement learning is so exciting and give you a foundation on which to build for the next couple of days as you learn more about exciting latest results in reinforcement learning. Now, reinforcement learning is all about making decisions and learning from the consequences of these decisions. And if, like me, you start to think about reinforcement learning a lot, you encounter reinforcement learning problems in your daily life almost constantly. You realize that there's so many decisions to make. What socks to put on in the morning. If you drive a car, how hard to press the gas pedal. Which session to attend at NeurIPS. Or what course of study to take. And a lot of those decisions we have to make under uncertainty. We have to sometimes try something and then learn from the consequences of those decisions. Now, as you learn more about reinforcement learning and think about over the next coming days, I would like to invite you to think about how you make decisions. For example, as you navigate this conference center, sometimes taking a wrong turn, maybe updating what you know about this space, and how by the end of the week you have started to become really familiar with it and you know where to go. So under those settings, how can we describe how an agent, for example, a person or some other agent, interacts with an environment, how it collects experience and learns from that experience? So reinforcement learning, briefly, is about decision-making and learning under uncertainty. It's a highly interdisciplinary endeavor. For example, reinforcement learning has connections to psychology, to neuroscience, for example. But today I will be focusing on a computational perspective. These other perspectives are very much represented at NeurIPS, and I invite you to take a look as you go through the conference and uncover some of those connections. Before we start and dive deep into reinforcement learning, I just want to acknowledge my amazing team at Microsoft Research. Here's a recent group photo of the team there. We are all based in Microsoft Research in Cambridge, in the UK, and you see the building there. And we together have the belief that computer games are a fantastic environment in which to push the state of the art in reinforcement learning. You see an example of Minecraft on which one of our main projects, Project Malmo, is built. And at the same time, we're driven by finding and developing new applications using reinforcement learning in games. For example, to enable new experiences for players and to make it easier for game developers to use reinforcement learning as part of the game development cycle. Now, for today, we have the following plan. First of all, I want to lay some foundations of reinforcement learning. We will look at the formalism that allowed the field to make progress over several decades and is still going very strong. We will look at two types of approaches to solving reinforcement learning problems, value function-based approaches, then look at exploration, and then the next type of approaches, policy gradient and actor-critic approaches. And then we will dive deeper in a couple of topics that are particularly close to my heart, looking at, for example, how to make progress towards generalization, how to use structure, models, and some new challenges that are driving research in reinforcement learning. The very foundation, or a really good starting point for the field, is the notion of a Markov decision process. Now, so-called sequential or multi-stage decision problems, which we look at in reinforcement learning today, have been studied for at least 200 years. The goal is to develop systematic approaches that can be applicable to the widest possible range of decisions and application areas. And in order to make progress towards those, the field needed to develop foundations, a type of model with structural assumptions that allow people to say something formal about whether a decision is, for example, optimal, or how an agent should behave when it had some uncertainty about the environment. If that is not given, then you can imagine a decision-making in settings where, for example, the environment constantly changes. And in those kinds of settings, it's really, really hard to make progress and talk about how we actually should be making decisions that have some notion of optimality and make progress. Now, one such structure, one such set of formal assumptions that allowed the field to make progress is the Markov decision process. The term was first coined by Bellman, and there were seminal papers by him in 53, 54, and 57. So with the Markov decision process structure, we have a simple model that has been incredibly successful, and it has driven research over the last 6+ decades. So let me start by introducing some of those assumptions that were made by Bellman in this technical report from 1953. So plainly, he laid out a functional approach where there were 3 basic assumptions. First, the state of the system would be described by some small set of parameters. Second, the effect of a decision is to transform the state and the parameters of that state into a similar set. And finally, and importantly, the past history of the system is of no importance in determining future actions, and that is the so-called Markov assumption. So usually, this set of assumptions, or the modern versions of those assumptions, is illustrated like this, by an agent that is interacting with some environment that initially is governed by unknown dynamics and unknown reward. The agent acts with some policy, and this policy is usually learnable. So as the agent starts to interact with the environment, it observes some state, just like Richard Bellman described. This state can be represented in many different ways. So for example, we could use a discrete or tabular representation where the agent is told, you're in state 1, then it takes an action, now you're in state 2, etc. Or the state could be described by some set of features. For example, whether it's currently facing a zombie or what position it has in the environment. Or the state could be represented in some kind of visual representation. For example, it could observe the current first-person view that we see in this example here. There are many different choices, and this choice is really important when someone wants to formulate a problem as a reinforcement learning problem, like we're doing here. Sorry, there's an error in the image here. Secondly, the agent takes an action. So the action has some influence on the state of the environment. And again, there are many different choices as to how we want to formulate those actions. So for example, we could give the agent discrete actions, for example, a small set, move north, east, southwest, or attack whatever is in front of you. It could be a continuous set of actions. So for example, acceleration in a certain direction. And all these choices have important effects on how learnable the task is going to be, how quickly the agent will be able to learn good behavior. So already here we see a trade-off. Should we give the agent a large set of low-level actions, which might make it slower to learn, or should we give it a smaller set of higher-level actions that learn faster, but maybe cannot learn as good a behavior as would eventually be possible using those lower-level actions? Finally, we have to select a reward function for the agent to optimize. Again, there are many different choices here. So for example, in this example here in the game of Minecraft, we could give the agent some positive reward while it is alive in order to encourage it to stay alive as long as possible. We could give it a negative reward for receiving damage, or we could give it a positive reward for dealing damage or for killing a zombie. And already, again, here you see that there's interesting trade-offs that the agents will have to learn. And the type of reward structure we pick will, again, give some indication of what that trade-off is going to be. For example, if we reward staying alive very highly, the agent may learn to run away from zombies. And in contrast, if we give it a high reward for killing a zombie, it may seek out danger and run towards zombies to try and kill them as quickly as possible. Again, the reward structure is a modeling choice that the practitioner has to make. As just indicated, it is a really important choice that will determine what behavior the agent will learn in this particular environment. Key assumptions here for the Markov process formulation are that the behavior policy of the agent is typically denoted by as a policy pi, which is a distribution of actions given the current state observation. The environment dynamics, as mentioned, are assumed to be unknown to the agent, and the environment is governed by, first of all, a transition function or transition dynamics, here denoted as T, and this is a probability distribution over successor states or next states, ST plus 1, given the current state ST and the action that the agent took. And so here in these dynamics, we can see our key assumption, the Markov assumption, where we assume that the environment is next state is purely determined by which state it was in before and the action that the agent took. That's an important simplifying assumption because when we develop approaches for solving reinforcement learning problems in the form of MDPs, we can assume that the agent's behavior policy can be independent of the interaction history that led it up to a given state, and it has to make a decision purely based on the state observation that it has currently received. Finally, we assume that there's a reward function here denoted as R, and again, the reward is a function of the previous state and the action that the agent took in the previous state. Again, it's independent of the history given the state and the action of the agent, and again, this is an implementation or this is a reflection of the Markov assumption that we're making here. Now, the Markov decision process is a very simple formalization of a reinforcement learning problem. I want to just note that there are many, many other formulations. Two of the more commonly used ones are, for example, the POMDP, or partially observable Markov decision process, which goes back to Leslie Kelbling, and they're really insightful results on how to take actions when, instead of observing the state directly, the agent only observes an observation that is governed by some observation model that depends on a state but doesn't entirely provide information about which state the agent is in. Another common formulation is that of a Markov game, which extends this notion to the assumption that there might be other agents interacting in the same environment. And that kind of assumption can give the agent, from its point of view, the perspective that the transition dynamics might be changing over time because they're affected by other agents' actions as well. Both of those formulations, again, make important assumptions about the structure of the environment, and those structural assumptions allow for innovation and progress in those areas. But despite the simplicity of the Markov decision process, it is a really powerful model. And again, in the thought experiment of thinking about you as a reinforcement learning agent over the next couple of days, I invite you to think about how you would formulate specific decisions that you have to make in terms of a Markov decision process. For example, in order to decide what session to attend tomorrow morning, what information would you put into the state in order to make the fulfill the Markov assumption? What is your action space, and then what is the reward? How would you learn from it in that setting? And Going through those kinds of thought experiments gives you a really impressive understanding of what kinds of things can be more easily formulated, how powerful this model is, and also where its limitations might be. Now, in addition to the structural assumptions we just made, we also need some notion of optimality. So what is our decision-making agent trying to accomplish as it interacts with the MDP? There are three formulations that are quite commonly used, and here I'm using this based on an excellent survey paper by Leslie Kelbling, Michael Littman, and Andrew Moore that was written in 1996, and if you're not familiar with it, I highly recommend it. It's a very readable and accessible introduction to reinforcement learning and a really good survey of many areas that are still very relevant today. So the first optimality criterion uses a model that is called the finite horizon model. In this model, we assume that the agent interacts with the MDP over a course of episodes, and the length of episodes is limited by some horizon t, which is fixed and known. In this finite horizon setting, the agent then needs to maximize the expected sum of rewards that it might be able to obtain in this environment. And you can see that written out here exactly. We want to optimize the expected sum from a time step 0, where the agent starts to interact with the environment, to our known horizon h, and we want to maximize the sum of rewards. An alternative formulation is the infinite horizon setting, shown here. And the key difference is that now the horizon is not known, but instead we assume that in principle the agent could interact with its environment indefinitely. In order to make sure that the sum of rewards can still be bounded in some way, we introduce a discount factor, here denoted by gamma, and this discount factor ensures that the agent's rewards that are observed at our current time step t are weighted higher than an equally large reward obtained later. And you can interpret this discount factor in a kind of probabilistic way by interpreting it as the probability that the interaction between agent and environment might end after each time step. Third, there's the average reward setting. And in this setting, we assume that we're interested in the long-term average reward. So in the limit of an infinite horizon, we want to get an understanding of what the steady state reward would be that the agent could obtain. When no additional information is given, then we will typically assume the infinite horizon setting, but there is a lot of progress in all three areas. For example, I think there are 4 papers that are giving new results in the average reward setting here at the conference this week. Oops. Sorry, there's a slight building issue here. Finally, we need to look at learning performance. So given our optimality criteria, how can we qualify or quantify whether a given algorithm is actually performing well? A first kind of performance we could look for is some notion of asymptotic convergence. So for example, you might see notation like this, where a policy is guaranteed to go to an optimal policy, here denoted by pi star, as the amount of samples, the amount of data goes to infinity. And this would be a really reassuring guarantee that tells us that in principle, if the agent was to collect an infinite amount of data, eventually it would learn a policy that is optimal. The second type of guarantee is called a PEG guarantee, and this denotes the speed of learning. So it bounds the number of mistakes that an agent can make before near optimal performance is reached. And so typically the kind of notation that you would see here is that the probability that the number of errors is greater than some bounded function, here denoted as f, which is a function of epsilon, or the size of the error, and the function of delta, which is the bound on the probability we want to give. This probability is lower than some small delta shown here. Now, this is a guarantee that's very common in other types of machine learning. It's not necessarily an ideal fit for reinforcement learning because it does not give us any guarantees about the quality of the policy that is learned while we're learning. So, for example, while learning, the agent might make small mistakes or very large mistakes, and a PEG guarantee wouldn't give us any information about which of the two is true. Third, a common type of guarantee is called regret bound. And this one does measure performance throughout learning. However, it does require some kind of oracle information or hindsight that gives us an information about what maximum reward would be possible at a given time step. And so regret is defined as the difference between the highest possible reward that could be achievable at a particular point in time minus the reward that was actually obtained by the agent at that time step. And so if this difference is 0, that would mean that we have no regret that the agent is able to perform optimally in that particular situation. Now, in a regret bound, we want to bound the sum over errors by sum bound B. Finally, one issue or one potential issue with regret is that as the agent learns better and better performance, it may still make mistakes, and with regret, there's no notion of whether there are many small mistakes or occasional major mistakes. So this could really be a safety issue where if the agent is generally performing well, but occasionally makes a dramatic error, then this would give us the same, in principle, regret as an agent that makes many, many, many small errors throughout learning. And so one new notion that was introduced that unifies PEG bounds and regret into uniform PEG was introduced by Christoph Dunn, Lattimore, and Brunskill in 2017. So this is a type of learning guarantee that could be particularly well suited for reinforcement learning agents. Now, beyond these guarantees, in the past few years, we have seen a lot of new work that is looking at reinforcement learning from a more empirical point of view. In those, typically we're interested in roughly agents that perform well as quickly as possible and that achieve high learning performance within some compute bound. So the notions that we're looking for there in empirical studies are not perfectly aligned with those guarantees that we're denoting here. Finally, as we close the formalization component, I want to point out the key reinforcement learning challenges that need to be addressed as we develop approaches to solving MDPs or reinforcement learning problems. First, the agent needs to balance exploration and exploitation. So as discussed in a reinforcement learning problem, the agent continuously interacts with an environment. And the first question that any reinforcement learning approach needs to answer is how the agent should interact while it is learning. For example, at a given stage, it should be exploring to find out what the consequences of new types of decisions could be. And at the same time, it might need to exploit the knowledge that it already has in order to achieve high performance throughout learning. Secondly, the agent needs to solve the problem of credit assignment. Given some sequence of interaction, it might at some point observe either a high positive or a strong negative reward. And now it needs to understand how the sequence of interactions that it has performed contributed to those. So for example, when the agent turned left or right, how strong of an effect did that have on the infinite sequence of rewards that it actually obtained? Finally, reinforcement learning agents, especially in complex scenarios, need to deal with function approximation. So we need to understand how agents can learn, for example, from high-dimensional observations, for example, pixel images or other representations, and solve, for example, the credit assignment problem in the face of those complex state observations. Right? So now we have formalized our reinforcement learning problem. Let's take a look at some of the approaches that are actually developed in order to solve these. The first type of approach goes back again to Richard Bellman and notion of dynamic programming that he developed. These come in the form of the so-called Bellman equations or Bellman optimality equations. And they're based on relatively simple observations. First of all, the first observation is that a complex problem can be solved by breaking it down into smaller problems. And that is exactly one of the insights that, Richard Bellman developed here. So for example, if we take this quantity, which is the so-called optimal state value function, denoted as V star of the current state ST. The state value function is denoted as the maximum over the set of available policies, or the best policy, that maximizes the expected discounted future reward, that exactly that optimality criterion that we defined previously. Now, this might be a quantity that is hard to optimize directly. But so one thing we can do is we can actually break that down into two components. First, we cut off the first part of this infinite sequence of rewards and denote this as the reward given the current state and the action selected by the policy, plus the remainder of the sequence. So the remainder of this gamma discounted sum of future rewards, where now the sum is over the transition dynamics and the value of the next state, V pi of ST plus 1, shown in green and in yellow. And this is a really fundamental insight that Bellman had there. This was possible based on the Markov assumption that he made, that now given this assumption, we can actually break this problem of making sequential decisions into these components. In Bellman's terms, when looking at dynamic programming, he actually looked at the scenario where the model or the MDP was known to the experimenter. So it's one where we directly had access to the transition function, so probability over ST plus 1 given ST and A, and the reward. And now given this model of the environment, using dynamic programming, we can directly compute all those sequences, all the components of these terms, and we can build up our solution to the optimal decision at a given point by going through the entire sequence of possible decisions, working out the value at each given state, and then as we work backwards in time, find the solution for our optimal value function, and then the optimal policy would take the optimal, the action that leads to the optimal state at every point in time. Now, as we look at the full reinforcement learning problem, as already mentioned, we now don't have a model available. So instead of using dynamic programming to find the optimal policy using the model of the MDP, the agent has to learn from interacting with the environment. And one key idea here is the notion of temporal differences, or TD error, developed by Richard Sutton. The temporal difference error is again defined based on the recursive relationship described by the Bellman equations. But as mentioned, this is now done in the model-free settings where the quantities are learned from data. If we observe some tuple of data, so for example, the state that the agent is in, the action it took, the reward that it's observed, as well as the next state, then we can observe that the following must hold. If we have an estimate of the value of state ST plus 1, it again needs to sum to the reward, or the expected reward that we obtained at this given time step, plus the remainder of the sequence, gamma plus the value of the next state. If not, if this is not an equality, then there's an error, and this is called the temporal difference error. We denote this here as delta. You can see this as exactly the difference between our estimate of the actually obtained reward plus the value of the next state, the discounted value of the next state, minus our current value estimate. Now, the observation is that in an interactive scenario, an agent can learn by minimizing this temporal difference error. This results in this simple update rule that's shown here, where whenever we observe, we observe a new state, we update the value of that state using the update rule here by backing up to the reward of that state plus the gamma discounted value of the next state. And this simple update rule is surprisingly powerful. One of the first results obtained using temporal difference learning was a key breakthrough in actually learning how to play board games. This is a first major accomplishment that caught people's imagination of what model-free reinforcement learning can achieve. In the work for TD Gamma, Gerald Tesoro developed TD Gammon, a system that learned by playing backgammon against itself. It used a function approximator, a neural network of 40 hidden units, and it updated its weights of this neural network using the temporal difference rule that I just showed you. And over the course of, I think on the order of hundreds of thousands training episodes, the system actually became so good that it played at the level of world-class champions in backgammon. And it actually changed the way backgammon is played, as experts found for example, new opening strategies that TD Gammon had developed that turned out to be better than the ones that had been used by experts in the past. Another approach that is using, or that is based on the idea of temporal differences is so-called Q-learning. Q-learning is based on a variant of the Bellman optimality equation that is defined for Q values, where Q values are not the value of the states that we have already seen, but the value of a state-action pair. And so it's defined as the expected reward that an agent would obtain by taking action AT in state ST and then following the optimal policy moving forward. So we can see that here denoted as the expectation over the optimal policy of the reward that is obtained for the current state action pair, plus the gamma discounted value of taking the best possible action in the next state. Again, based on this definition, we can define a temporal difference error shown here. And this gives rise to a very simple algorithm that is called the Q-learning algorithm. So here in Q-learning, we observe for each episode an initial state as 0. Then for each step in that episode, we take an action A using our current estimate of the Q value for that action in that state. For example, we can use a strategy called Epsilon greedy, where we take the optimal strategy 1 minus epsilon % of the time and a uniform random decision otherwise. We take this action, observe the next reward and state, and then we update our Q value estimates given the rule that I just showed you. What's interesting for Q-learning that was developed by Watkins and then analyzed further by Peter Dayan and Watkins in 1992 is that for this algorithm, there are actually convergence guarantees that are known and that were developed in 92. So for Q-learning in a tabular setting, we know that in the limit of infinite data, Q-learning actually converges provably to the optimal policy, as long as while it is operating, it has a chance, a non-zero probability of taking every action infinitely often. And so this is a powerful guarantee in the tabular setting. There are quite new results for Q-learning as well. So as recently as last year at NeurIPS, a team consisting of Chi Jin, Alan Chu, Bubek, and Jordan answered the question of whether Q-learning is provably efficient. And they were able to derive regret bounds for Q-learning that show that in the tabular setting, this algorithm is indeed sample efficient. Now, to illustrate Q-learning and how it actually works, I want to show you an example that is using Project Malmo, the game experimentation platform that my team built on top of the game Minecraft and released in 2016. In case you're not familiar with this, Project Malmo is an open source experimentation platform. It is open-ended, so you can construct a wide variety of tasks for an agent to solve. You can select the observation space, action space, and reward structure to the agent. And so this allows a very wide range of experimentation scenarios that can maybe support your research. So I recommend you to check that out. Here we will look at a very simple example that implements a classic reinforcement learning task. In this case, it is taken from the Sutton and Bartow book that was in its new edition from 2018. So this is a cliff-walking task where an agent interacts with an environment. There's a positive reward when it reaches a diamond in the far corner, and a negative reward whenever it decides to jump into lava. In this example, the representation that the agent observes is actually tabular. So we can represent this as follows, where the agent, whenever it is in a state, you can imagine it getting a number of the state. So for example, it's told that currently you are in state 2, and you have 4 actions available. So at every point in time, the agent can go north, south, east, west. The agent doesn't know the spatial configurations, so at every point in time, it needs to, or at every state, it needs to experiment to figure out which actions lead to what consequences in what state. Early on in learning, the Q table might look like what's shown over here. For example, the agent might have already fallen in lava a few times. You can see some red dots that indicate its current negative Q value estimates. And there are other areas that are more neutral, where it hasn't suffered any negative consequences yet. And so as we run this, initially, this is what happens. The agent has to learn from trial and error. So initially, there will be a lot of actions that have negative outcomes. As the agent continues to explore the environment, it accumulates knowledge here in the form of this tabular representation as shown here. And you can see that at some point it has found the diamond in the far back, and it's starting to propagate backwards through the structure the positive outcome that it has observed. And so after about 10 minutes of training over here, the agent has nearly converged to an optimal policy. But now, of course, this wouldn't be as interesting as it is today if we couldn't deal with function approximation. So in the next section, we're going to look at initially how Q-learning can be applied with function approximation. The principle is actually quite simple. So you remember the temporal difference error that we defined earlier. We can exactly use this temporal difference error and minimize it if we have a more complex function approximator. So in the case shown here, our Q value estimate is not the tabular kind of individual estimate for each state and each action separately that we've seen before, but instead now we have a Q function that is parameterized by some parameters theta, and these parameters are learned in order to find a general function that characterizes the value of taking an action in some kind of higher dimensional state. So as mentioned, we can turn this into an optimization problem and minimize the loss on the temporal difference error. This principle of using function approximation and turning Q-learning into an approach that uses function approximation was actually already laid out when Watkins first proposed Q-learning and the Q-learning algorithm. But for a very long time, there was a big problem of actually getting this algorithm to learn in a stable manner when using function approximation. The key challenge was stability. And so in the Sutton and Bartow book, they actually coined this notion of the deadly triad. They said that whenever we use an off-policy learning algorithm, and Q-learning is off-policy because we're actually using our estimates to learn about the optimal policy, not the one that the agent is currently following. When we use flexible function approximations, so for example, when the Q function is parameterized using a deep neural network or another complex function approximator, and when we use bootstrapping, which we're doing here because, as mentioned, our Q value estimate for the current state is bootstrapped using the value estimate for the next state that we have encountered. In the face of all three, learning is unstable, and it was actually shown that it will and can and will diverge. And I'm showing some references on that here. Now, the first really successful, stable application of Q-learning was the DQN algorithm, which very famously solved or learned to play 49 different Atari games from visual observations. And there are key insights here in how learning was finally stabilized. First of all, DQN uses an experience replay buffer. This had already been proposed in '93, but in this case here, the replay buffer was then used for mini-batch stochastic gradient descent, where a lot of new tools had been developed to do this effectively and efficiently on GPUs at large scale. A second step to stabilize learning in DQN was to separate out a target network that would stabilize the optimization targets. So you can look at the temporal difference error over here, and you'll see that there are two different versions of the parameter vector theta. The first one, shown in red, is denoted as theta t, theta prime, and this one is the so-called target network, which is occasionally formed in the form of a snapshot of our currently learned Q function, and it's held static for a certain amount of time, so that for that period of time, the optimization targets don't change as quickly as they otherwise would. There's now some follow-up work where the target network is slowly changing over time and slowly trailing the original Q function, and both of those have a strong stabilizing effect. The third innovation that also greatly improved stability of learning was that the temporal difference error was clipped to a range of -1 and 1. So these are the three ingredients that actually led to stable Q learning. There's a great blog post on this, so if you want to learn more about this and dive into a little bit more detail, I highly recommend this, and it also has code that shows how DQN can be implemented. Of course, many of you know the results of this. So here, in this work by Nie et al. In 2015, the same training setup was used over all 49 Atari games that were addressed in this work. And this resulted in the very impressive result that using the setup, learning from visual state observations, the agent was able to, or the set of 49 agents was able to reach superhuman scores on 75% of those. Since then, since 2015, there has been a huge amount of follow-up work, and I just want to highlight a few examples here. Van Hasselt and colleagues introduced double Q learning, which is an approach that reduces bias of the Q value estimates. Anschel et al. In 2017 introduced average Q learning, which reduces the variance of Q value estimates. Andrei Chovitz in 2017 looked further at the replay buffer that was used and introduced hindsight experience replay, which would reprioritize the experience that was collected by the agent. Dabney et al. Had a very interesting, or started a very interesting line of work in distributional RL, where the Q function is trained not to estimate the expected return, but instead where it learns a distribution over Q values, where the distribution is induced by the stochasticity of the MDP, or by the experience that the agent can observe. And there was a lot of work in scaling this up. So Apex, for example, is work by Horgan et al. In 2018, where they managed to scale up an initial DQN by dramatically setting up a very large system where the replay buffer was distributed so that updates to the learner could be parallelized at a massive scale. Again, if this is something of interest, I highly recommend David Silver's ICML tutorial, which is exclusively focusing on deep reinforcement learning. So now let's look at an example. Here's an example where we used DQN to learn to navigate Minecraft from pixel images. On the slide here in the top left corner, you see the set of observations that the agent observes. So this is the current frame, and the past 4 frames actually observed by the agent. You can also see the agent's current Q value estimates shown here. The agent has 3 actions available: turn left, turn right, and move forward. And you can see that there's a very strong negative estimate for the move forward action, which is fair enough, given that the agent is currently facing a pool of lava. And so we can see, as the agent navigates this environment, its Q value estimates are changing, and it's able to successfully navigate to the goal. Now, using function approximation allows us to gain more insights into, for example, how agents perceive their environment. And so one very early work in this stage was looking at this with our intern Lydia Liu here, where we found that agents that were trained in a set of lava mazes like the ones shown here, but not a single task, but a distribution over lava mazes, would actually learn recognizable clusters, where the agent would separate out clusters of observations where it was facing danger. So that was an interesting first insight that the agent was actually learning to generalize over different types of environments. Before moving to policy gradient methods, I want to say a little bit more about exploration. In the examples so far, we have only looked at how the agent can learn from experience, how it can update its Q-value estimates using temporal difference errors in order to solve the credit assignment problem. But we still haven't talked about how the agent should actually interact as it is learning. I want to point out a few common approaches, and many of those approaches to exploration have been initially developed and pushed forward in a setting that is more restricted than the MDP setting, and that's called the Bandit setting. In a Bandit setting, you can imagine this like an MDP setting, but here the action that an agent takes in a given state does not affect the state that it observes next. So you can imagine this as a setting where the state is sampled uniformly at random from a state distribution, no matter what the previous state action pair was. This kind of setting works well, for example, in a recommendation setting where, let's say, you have a news recommender website. Every time a new user visits that website, you want to recommend an article that might be relevant for that user. And so you select an action every time. You get some reward for that action, but then the next user coming in is not affected by the recommendations that you made to previous users. So now, if we look at a first very simple type of approach, we can look at an example of optimistic initialization. And this is actually one component that we used in the tabular Q-learning example that I just showed you. If, for example, some upper bound on the reward is known, then we can, or on the Q value is known, then we can initialize all our state value estimates to that upper bound. And this means that the agent will be drawn into areas that it hasn't explored so far. This very simple exploration strategy can still lead to interesting new observations. For example, this is work that we presented at the exploration in reinforcement learning workshop last year, where we looked at an example that's a classic deep exploration problem, or a classic hard exploration problem in the reinforcement learning literature, the so-called mountain car problem. In this problem, you start with an underpowered car at the bottom of the hill. And the goal is to navigate to the location indicated by a star here. In order to reach this goal, because the car is underpowered, it needs to go back and forth until it has gained enough momentum so that it can exit this valley. In this scenario, the agent does not get any positive reward until it has actually navigated to the goal. So it is quite a hard problem where if the agent was to explore uniformly at random, it would be hard to accidentally happen across a strategy that actually works for the setting. Now, interestingly here, we found that depending on the kind of function approximator used, the agent would learn with very, very different dynamics. You can show on those plots here the kind of coverage of the state distribution that was obtained by the agent. And this was done for different function approximators at a setting where no exploration at all was used. So we initialized the network, the function approximator, and then just followed the greedy policy. With the linear function approximator, shown all the way on the left, the agent did not learn as successful strategy. But as the depth and complexity of the function approximator increased, the agent was actually drawn to the successful states, and so it would systematically explore this environment and kind of interestingly kind of showing that there is an interaction here between how the function approximator is optimized and how it generalizes over those states in the face of optimistic initialization. Another very commonly used approach is the so-called epsilon greedy approach, which I already mentioned. It's a very simple strategy where the agent uses the exploitative or greedy action with probability 1 minus epsilon, and the remainder of the time it samples a action that is sampled uniformly at random, as shown here. In this example here, I'm indicating the greedy action, and the remainder of the time, the agent would select uniformly from all actions. And you can already see an issue with this strategy. If we're actually interested in performance while training, then the agent maybe should make a difference between an action that currently has a very strongly negative value estimate and one that seems almost as good as the current optimal action. Strategies that allow this are, for example, the Softmax strategy. So this one pushes the current action preferences through a Softmax, and this gives us a distribution of our actions to sample from. This allows us to create a distribution where actions are sampled based on their probability of being optimal. A very systematic approach has been widely explored in the Bandit literature. It's called the upper confidence bound strategy. So in this one, the agent not only maintains an estimate of the current values, but it also maintains an estimate of the upper bound, for example, on a 95% confidence interval over that action. And it then selects the action with the highest upper bound deterministically. So you can imagine this as, for example, if we have a very high level of uncertainty for the value of the middle action here, then over time that action would be selected more often, which would allow the agent to get a more accurate estimate of its of the value of that particular action in that state. And the confidence bound would decrease until maybe it crosses with the next highest action, or maybe it turns out to be the optimal action for the state. Finally, a strategy that is quite easy to implement but harder to analyze is one called posterior sampling. In this one, the agent has to maintain a distribution over possible problems, for example, bandit problems, under its current estimates. And at time t, it samples from this distribution over possible environments and then takes the action that is optimal for the sample that it's drawn. Now, in the bandit setting, that is quite easy to do. So, for example, if you have 3 actions where you don't need to worry about the long-term consequences of these actions, you can draw samples from the value distributions over those actions, and then select the action that has the highest value over those. In the MDP setting, we have to actually reason over the consequences, over the sequential dependencies of actions. And this is a setting where using posterior sampling becomes much harder. A line of work that has led to really interesting insights in this space is one by Ian Osband and his colleagues. And one piece of work that extended posterior sampling to the full reinforcement learning, to the MDP setting, was published in 2016, where they proposed an idea of Bootstrap DQN. So as mentioned, in posterior sampling, you maintain a full distribution over the possible environments. So in this case, over the possible Q functions that might be consistent with the current environment. At a given point in time, you then sample from those possible Q functions and take the action that is optimal according to your sample. The key innovation here was that Ian Osband showed how you can approximate your uncertainty over Q using deep ensembles. And initially, that was approached by extending a DQN estimator with several heads, as shown in the figure here. And those heads would give you an approximate uncertainty estimate. So they would each be trained using different subsets of the experience that the agent has collected. And then whenever a sample from that Q distribution was needed, you would select one of those heads, obtain the bootstrap sample from this. And so over time, as more experience is collected, this would converge to an approximate version of the Q value distribution. This was extended in 2018, where, again, Ian Osborne and his colleagues showed that it was important to incorporate some kind of prior into Bootstrap DQN. So in the previous version, all the uncertainty over the MDP, all the uncertainty over the Q function was purely driven by the data, and there was no way previously of injecting prior information into the setting. In this follow-up work, Osborne and colleagues showed that it is important to incorporate prior information, and depending on that informed prior, they were able to show that much more systematic exploration could be learned in those settings. Here in this figure, I'm showing an example where in a complex card pull setting where the agent starts with a pendulum in the downward position. It has to learn to balance this pendulum and only gets reward once the pendulum is correctly balanced upright. In this complex exploration setting, the agent with Bootstrap DQN and a correctly informed randomized prior function would be the only one that successfully solved this scenario. Here at this conference, we're presenting follow-up work that sheds more light into how randomized value functions can be used for deep exploration. The idea here, which was developed in work by our former intern Dave Jens, together with Jerry Ron and many of our collaborators, is to express uncertainty over the Q function in terms of a successor representation or successor features. Now, the notion of successor features was introduced by Peter Dayan in '93, and you can think of it as a learned estimate of the transition function that can be updated using the temporal difference method. So if you imagine temporal difference learning, at every point in time, you would use estimates to not only regress to the reward estimates, but also to regress towards the features of the successor states. And so this gives you this representation of the steady state transitions from the given state. Now, in this work, we show that on top of the successor representation, we can use Bayesian linear regression to learn approximate uncertainty estimates over the Q function. This is a principled approach, and it shows very good results empirically. So, for example, here in an example of a chain MDP, where the agent has to learn a very, very long sequence of decisions in order to get to the end of this, tree MDP, we were able to show that successor uncertainties roughly matches the results that can be obtained using the Bootstrap DQN plus prior, but at dramatically better computational efficiency. The team was also able to run this on all 49 Atari games that were used in the DQN work and dramatically improved performance over previous exploration approaches. And so in the plot here, I'm showing a comparison where the bar is positive and blue when successor uncertainties outperform previous approaches, and red when for games where it underperformed. And so we can see that successor uncertainties learns very effective exploration strategies for all those 49 Atari games in a setting with high-dimensional observations. If you would like to learn more about this work, Dave will be presenting this together with many of our colleagues in the morning poster session tomorrow morning, and it's going to be poster 198. With this, I think it's time for a short break. So if you have any quick questions, you can move to the microphones to ask them. All right. So I got a question up here in front. The question was about long sequences of dependencies where, for example, an action right now might have consequences very, very far ahead in the future. So the example was in the zombie example. An action now might have an immediate high payoff. For example, I could hit the zombie right now, or let's say I could move further away, get armor and a better sword, and then kill a lot of zombies far in the future. The question was, does that accurately kind of capture? Okay, close enough. And so the question was why people in those settings stick to the MDP formulation instead of maybe using approaches that would more explicitly consider that sequence of events. In the approaches to the MDP formulation, you can actually use methods that very explicitly conduct updates that take the temporal structure into account. I only discussed TD0 right now, which is the temporal difference learning method that only updates the immediate next state. But there is another kind of whole family of approaches called TD lambda, where lambda can be used to weigh updates across a very, very long sequence, and that's called eligibility traces. So in this setting, for example, we can tune lambda in order to very, very quickly propagate information through the sequence, through a trajectory, and that can lead to much faster learning at the expense of more computational cost for each individual example. So, yeah, good.
No. Hi, I have a question. I wonder, on the previous slide, you showed a method of exploration. I wonder if you could comment on comparison between that and Aziza Denisheli's Bayesian DQN?
Say again, between the?
Between this method and Aziza Denisheli's Bayesian DQN?
I'm not quite sure whether you mean the method that's labeled UBE here in the slide. So again, this is an approach that estimates uncertainty over Q values, but doesn't explicitly take into account the transition probabilities in this setting. And so it's not as principled as the approach we're proposing here. Again, on Atari games, we're showing that we're exceeding performance of that method by a large margin.
Hello. I have a question here. Thanks for the presentation. It seems like all of these are based on one fundamental assumption for Markov, like the Markov process and so on and so forth. But there are a lot of games or activities in general that they do not hold that assumption. And we try to put these information into states to get rid of that contradictions. For example, in chess, if you get check and you cannot, castle in future, you could go on, and the very end of the game, you cannot castle because the state was changed in like 100 states ago or 100 moves ago. We are all trying to put all of this information into replay buffer and, I don't know, into a state somehow to get rid of these contradiction. Is there any other way to think about it rather than Markov processes and all of those Markov assumptions to have a more rigorous umbrella on top of these contradictions?
Thanks for the question. So in the chess example, I'm not quite sure I follow your reasoning. Usually the assumption is that chess is fully observed because all information relevant to a current decision is actually given in the board configuration. So if we can observe the board configuration, the state is fully observable. There are settings where full observability is not easily created. So for example, in a game like poker, there is a part of the state that, as the rule of the game, is not observed, and those are maybe your opponent's cards. In those settings, a POMDP setting would be appropriate, so partially observable Markov decision problem setting. In that setting, again, a lot of progress has been made over the past decades and could easily be the subject of an entire lecture or course of study on its own. So I just want to briefly comment on this. In a POMDP setting, you typically have to maintain a belief state, and that belief state is a distribution over states that the agent might find itself in. It then needs to learn an optimal policy in this much higher dimensional belief state, and this is kind of the optimal solutions for this are known in principle, but a key challenge is to make this tractable and computationally feasible in any high-dimensional scenarios. At the same time, progress is constantly made, and I think with some of the tools on function approximation methods that are currently becoming available, we're seeing a lot of progress over this. And there have been key results, for example, in poker, that very successfully learn effective strategies in those high-dimensional, partially observable Markov decision processes. All right, thank you so much for your questions. There will be more time for questions at the end of the tutorial. Let's move forward for now. So in the previous slides, I introduced one type of solutions towards reinforcement learning problems based on value function approximation. In the next section, I want to look at an alternative or maybe a complementary view which directly focuses on optimizing the agent's policy rather than deriving the policy from current value estimates. And so I want to start here by presenting a simple algorithm, a simple update rule that actually achieves this. And based on this policy gradient rule, again, a lot of progress has been made, especially in applications with continuous action spaces. And robotics is a prime domain for an example application area with continuous action spaces. So the simple update rule here was proposed in '92. It was actually a family of approaches called the reinforce framework. And so let's step through this algorithm and try to understand how this works. This is an algorithm that proceeds in episodes, and in each episode, we assume that an agent interacts with the environment using its current behavior policy, here denoted by pi theta, of distribution over actions A given the current state. This policy is parameterized by a parameter vector theta, and so we could assume this, for example, to be parameterized as a neural network. Now, for each step along the trajectory that the agent has observed, we now update the parameters of the policy. First, we need to compute the return that the agent was able to obtain by using its current policy in the current state. And this estimate is going to be summed over all the remaining steps all the way until the end of the episode. And so this gives us an unbiased estimate of the remaining episode return under the current policy pi theta. Second, Williams proposed to subtract a baseline. This isn't crucial or not necessary, but it does lower the variance of our return estimates, and so it leads to faster learning in practice. A good baseline for reducing variance is, for example, the return of the entire episode. And so you can, or the average episode return, and you can think of this consequently as a kind of advantage function. So for each step along this trajectory, the advantage function tells you how relatively good this action was compared to the average return in the rest of the trajectory. Finally, we come to the key step. We actually update our policy parameters. And so here in this step, we compute the gradients with respect to the policy parameters using the estimator shown here. Now, initially, this estimator was justified heuristically and showed good performance. But based on work by Rich Sutton and his colleagues in 2000, they developed the policy gradient theory, which actually shows that this quantity, this gradient G hat here, is an unbiased estimate of the objective that is shown here. So if we start with our overall objective, J theta, as the sum over all trajectories, where we want to weigh the probability of each trajectory by the return that we get for that trajectory, then this is a very kind of clear objective that intuitively shows that we want the policy gradient method to move away from poorly performing trajectories and push the policy parameters towards trajectories that have high return. If we take the gradient of this, we can see the expression here, and the policy gradient theorem shows that this is actually that the estimator G hat that we're showing on the algorithm side is an unbiased estimate of this quantity. There's a nice and short derivation of this, so if you're interested in understanding this in more detail, I suggest that you take a look at Sutton's paper there, which is very readable. Looking at modern actor-critic approaches in comparison to this update rule, they use a learned estimate of the advantage instead of the one that is used using Monte Carlo sampling. And so the actor-critic approaches here learn their value estimate very much in line with how, for example, Q-value estimates are learned in DQN. And so we can see how this can be combined with insights into how to stabilize the learning of value estimates to get stable estimates of the so-called critic that criticizes the current policy, and combining this with this vanilla version of policy gradient. A nice overview of policy gradient methods for deep reinforcement learning was given by Peter Abil and John Schulman at NeurIPS 2016. That's a great source of information for policy gradient methods. But let's take a quick look at a couple of variants, of modern variants of actor-critic approaches. When developing these techniques, there's typically a challenge between the kind of simple update rule that I showed previously and the need to use modern optimization machinery in order to obtain stable learning updates. And so these algorithms typically need to balance between learning speed and stability. Very fundamental insights in this space were made by Asham Kakada and John Langford in their 2002 paper, which focuses on conservative policy iteration. This kind of noted this challenge that in order to get stable updates, you need to often get value estimates for a part of the state space or action space that hasn't been very well explored in the past, and then those estimates may be very poor. So you need to balance between moving to the space that has potential high value and actually being conservative about how far to update, because the value estimates in that area of the space may be very poor. In this paper here, the authors found a surrogate objective that could optimize and actually obtained monotonic improvement guarantees, but this was with a very specific construction of the state distribution that could be used in order to get update estimates. Building on this, John Schulman and his colleagues developed trust region policy optimization, and this approximated the kind of understanding or the CPI objective with a so-called trust region constraint. This constrained the update of the policy to lie within a certain bound of the current policy in order to ensure that the policy wouldn't be moving too far from the area where its estimates were reliable. A further heuristic approximation to this was developed again by Schulman and his colleagues in 2017, called proximal policy optimization. This approach replaced the TRPO constraint with a soft KL, or Kullback-Leibler penalty, and additionally clipped the update errors, the optimization errors, in order to further improve stability. This method was a very computationally efficient approximation that performs similar to TRPO in terms of sample efficiency, but is much more computationally efficient. Just to give you a sense of how some of these perform, this is a selected plot from the PPO paper where the results are shown for a Mojoku task called Half Cheetah. In the Half Cheetah task, the task is to get an agent shown here in the Mojoku simulator to apply forces to its actuators in order to stably move the cheetah forward in a given direction. And so you can see that, for example, in this setting, PPO learns the task much, much faster than competing approaches, competing baselines. We can also see that vanilla policy gradient in this setting is not performing too poorly compared to other modern approaches. The next approach I want to mention is a very recently developed one by Harnoria and his colleagues called soft actor critic. In this approach, learning is stabilized by jointly maximizing expected reward and at the same time maximizing policy entropy, which is based on the maximum entropy reinforcement learning framework by Brian Siebert and colleagues. This leads to a very stable approach, and in addition to this update rule, soft actor critic uses a lot of insights that were developed, for example, in the successors to DQN. So, for example, the method also uses a replay buffer, target network, etc., for learning the critic estimates, and that is combined with this very efficient policy gradient update. Again, to give you just a sense of the results here, SAC is the curve shown in orange, and so you can see over different Mojoku tasks, it's performing very competitively. Finally, in the policy gradient space, I want to briefly touch on a work that we'll be presenting here at NeurIPS called Optimistic Actor Critic. This one focuses on the question of how to do systematic exploration in modern actor critic approaches. The key insight is that existing previous actor critic approaches seem to be exploring conservatively. So because they have to constrain their policy updates and the policy with which they collect samples in order to achieve stable optimization, it seems that they are not exploring as aggressively as they could. The key insight here is that it is actually possible to develop a more principled exploration approach which uses the principle of optimism in the face of uncertainty. And so this is based on the UCB upper confidence bound exploration strategy that I mentioned earlier, where we're able to derive a bound that weighs the current mean estimate of the Q function, combines the mean estimate of the Q function with a covariance matrix that appropriately lets us derive an upper confidence bound on the current policy. If you would like to learn more about this work, this will be presented in tomorrow afternoon's Spotlight session, track 3, session 2, and also in the afternoon poster session tomorrow. Just a quick key result here. We can show that optimistic exploration leads to efficient and stable learning in actor-critic approaches. And here we're showing a comparison between OSC and SAC on the very challenging humanoid Mojoku task, which is the most challenging of the benchmark tasks that have been proposed so far. Now, before diving into the next topics, I want to briefly touch on some of the reinforcement learning applications where we've seen a lot of progress towards practical applications in the past years. We have seen kind of on many settings that in games, reinforcement learning algorithms can perform well, but in many settings, those are the ones where a model is actually given. So in settings where no model of the environment is available, it's been much harder to push towards real-world applications. One example application is the so-called personalizer, which is a service on Azure that is actually serving millions of customers with personalized recommendation results, such as in the news recommendation setting that I mentioned earlier. This is based on applications of bandit approaches. So it's the setting where we kind of well understand the problem of exploration, exploitation, and possible solutions, and where within the bandit setting, function approximation is well understood. It's also in a personalization setting where data from many millions of users can be used in order to learn good estimates of how good the quality of, for example, a news recommendation item is. In robotics, very impressive results have been achieved, for example, by the group at Berkeley, shown here. And a lot of details about applications and kind of issues in the robotics space are discussed in this excellent ICML 2017 tutorial shown here, which was given by Chelsea Finn and Sergey Levin. Again, it seems that in the robotics setting, a lot of progress is made in settings where a simulator is available. Mujoku is maybe not the most accurate robotics simulator, but this is a setting where a lot of the kind of modern reinforcement learning approaches can be developed and empirically pushed further. A third application area that I've personally been really impressed by is by Emma Brunskill and her group at Stanford. An amazing tutorial was given by Emma Brunskill at NeurIPS 2017 with a focus on reinforcement learning for the people and or by the people. It seems to me that in a lot of those applications where we're currently successful are the settings where a large amount of data is available, either in real life or in simulation. But a key challenge, a key open question is how we can push reinforcement learning approaches towards applications where sample efficiency really matters. And so the key question here is how can we develop dramatically more sample-efficient algorithms that could, for example, learn to directly adapt to an individual user. Imagine a robot that can understand the specific goals that you are setting for an application and learn safely and efficiently to address those goals. Or a tutoring system where the system is able to very, very rapidly adapt to an individual student and maximize their learning path. Or a setting even in a game where for a given player, an agent is able to very, very quickly adapt to what the player is trying to do. For example, in order to give them a more fun, more exciting player experience. Those questions raise the question how we can kind of move forward and make sure that the algorithms that we develop are more sample efficient and move in this direction where they can be applied where we have very little data. A further example there would be the healthcare setting. How can we develop reinforcement learning algorithms that are able to personalize healthcare? So, for example, provide suggestions on what treatment should be followed for an individual patient. So here in the next couple of slides, I want to point out some of the paths that I see towards more and more sample-efficient reinforcement learning. And to me, those are some of the areas where reinforcement learning research is the most exciting right now. One possible take on more sample-efficient learning is under the notion of generalization. So if you assume that in a reinforcement learning setting, let's say we have relatively little data available for one individual task, but at the same time, we have a large number of similar related tasks that we can use in order to learn a general solution, then the hope is that for each new individual task, we may be able to learn a new strategy relatively quickly with few samples. So over the past, kind of generalization in reinforcement learning has been addressed for a very long period of time. So, for example, even the successor features that I mentioned earlier, developed by Peter Dayan, those were kind of a direction to understand how agents could generalize very quickly. And recently, it has turned out that indeed the successor representation can be used for very rapid adaptation. For example, in the work shown here by Barreto and his colleagues, it was shown that using the successor representation, an agent could very, very rapidly adapt to a new reward function that hasn't been seen at training time. Another piece of work that I want to highlight is by Karl Kobbe and colleagues, where they looked at kind of really systematically evaluating what number of related tasks would be necessary in order to obtain effective generalization using modern reinforcement learning approaches. The interesting insight here was that the number of tasks is much, much higher than what had been previously assumed. So if you see those plots here, there's a log scale that shows the number of training levels for a given simple platformer game that were needed until the agent was actually able to solve held-out test levels that hadn't been used for training. And you can see here that this is in the order of tens of thousands of levels that were necessary before the agent could actually learn an effective generalizable policy. Some of those recently proposed benchmarks were also benchmarks that we have used in our own work and work with my colleagues. I'm showing two that we have recently used over here. The first such benchmarks is the so-called multi-room environment by Maxime Chevalier-Bossuet and her colleagues. And this is a series of rooms that are procedurally generated, where an agent, indicated by the red triangle here, has to navigate to the green square. The interesting twist is that none of those rooms is seen twice by the agent. So in order to solve this task, it has to genuinely learn a generalizable strategy for navigating rooms, rather than simply memorizing a given scenario. The second benchmark we used is the one by Kobbe and his colleagues, which I already mentioned previously, and it's the so-called coin run platformer game. So in this procedurally generated set of platformer games, an agent is always in the middle of the screen. It's denoted by this little character here, which can be represented in different colors as well. There's always a single coin somewhere in this environment, and the task of the agent is to navigate through this, avoid dangers like this enemy over here, and navigate to the single coin, pick it up in order to get the reward. As you can see, the configuration of these levels is quite diverse. There are many different visual representations, so this is a good benchmark for testing to what degree an agent can actually generalize. The authors here also evaluated kind of the most common regularization approaches that had been proposed for achieving better generalization in supervised learning, and had very interesting insights on how those compare to each other. Now, in the work that we're presenting here, which was led by our former intern, Max Eagle, we look at how to specifically create regularization approaches that are effective in the reinforcement learning setting. The key insight here is that regularization should not be applied blindly to the entire estimator, but instead that we should be selective about where regularization is applied. We can see here in this case, the objective that's optimized by PPO, that the policy is used in different components of this objective. Shown in green is the rollout policy that we actually use to collect data, and shown in blue are the components where the policy is actually used in order to compute gradient updates. Now, regularization needs to be applied to the components where the gradient is computed, but we can suppress regularization, often introduced in the form as noise, in the actual behavior policy, and that can lead to lower variance behavior during learning, and it can be used to control exploration behavior of the agent. The second insight is that when we combine a diverse range of regularization approaches with the selective strategy, and a regularization using an information bottleneck is actually particularly effective. And we think this is because in the low data regime, this allows the agent to learn a relatively low dimensional representation of the policy. We get very good performance on these. So in the multi-room scenario that we showed previously, the proposed regularization approach is the only one that is able to solve a sizable number of 3-room mazes, and it's dramatically outperforming previous approaches on smaller mazes as well. And here's a qualitative example from the platformer game that I showed you earlier, where we see that with previous regularization approaches, the agent's policy is noisy, it makes mistakes, but with the proposed strategy, it's able to solve scenarios like the one shown here. Again, if you want to learn more about this work will be presented in the Thursday morning poster session. Also relevant to this area is the workshop on Saturday that focuses on learning transferable skills. And for example, Carl will be presenting their recent work on generalization in the CoinRun platform. So that should be a really exciting event if you're interested in learning more about generalization and learning generalizable and transferable skills. A second approach to achieving better sample efficiency in reinforcement learning is to impose and exploit some form of structure. One form of using structure is again related to the multitask setup that I previously mentioned. And one very successful formulation over the past years has been so-called meta-learning. A way in which I like to think about meta-learning is, for example, as a kind of augmented MDP formulation, such as shown here. You can think of the simplest possible way to kind of augment the MDP formulation is if there's a single latent variable, shown here as mi, which governs or expresses how different MDPs in a multitask setting are related to each other. And so you can think of this as capturing, for example, how the transition dynamics or the reward structure, or maybe both, could be varying across those different tasks. But we would assume that there is structure that makes this variation fairly low-dimensional. So for example, you can think of a car driving example. In every car, maybe the steering and acceleration may behave slightly differently, but there are very few parameters that you need to figure out in order to understand how to drive a car that you've never driven before. And so intuitively, that could be one way of understanding how to learn very rapidly from experience collected in related tasks. A very, very influential approach to meta-learning that has been proposed in 2017 is work led by Chelsea Finn, and it's the so-called MAML approach, model-agnostic meta-learning. This is a very flexible approach to meta-learning that is based on second-order gradient descent in the following two-step procedure. In this setting, there's the assumption that the agent at training time has access to a large number of training tasks. And based on those training tasks, it can learn an update rule. It can learn how to update its parameters to very, very quickly adapt to a new task. And so on the kind of inner loop, the agent computes an update to the policy or value function parameters based on the new sample of training tasks. And in the outer loop, it is backpropagating through that update in order to understand what its parameters should have been so that it could have adapted more rapidly to this new set of tasks. At test time, then, the agent again observes a new set of tasks, and because it has learned a very central kind of or a very good initialization, it is now able to update to this new task very, very rapidly with only a few gradient update steps. If you want to learn more about meta-learning approaches, I recommend this fantastic meta-learning tutorial that was given by ICML earlier this year by Chelsea Finn and Sergey Levin. Some of our recent work in this area is based on MAML, and it is looking at more specifically how we can improve over MAML in a setting where tasks are related through a low-dimensional embedding, as I showed earlier. In this kind of formulation, you can think of this as task identification. At test time, you may not have to actually update all the parameters, but you might only need a small number of context parameters that identify the task correctly and that allow the agent to now interact with this new task. So compared to MAML, the approach that we're proposing is to separate out context parameters from the rest of the network, and at test time only update those context parameters in order to do very rapid task identification. So a quick overview of how that works. We have the context parameters, which in a way are a learned task-specific input parameter vector. These are updated at test time via gradient descent, and these represent the task embedding. There are also the normal network parameters, which are shared across tasks. Those are trained during meta training and then fixed at test time. Very briefly, this is how this approach works. Again, in the half cheetah directions example, we can show that the agent is able to guard against overfitting because it's now updating a much smaller set of parameters, so achieves higher performance more rapidly at test time. We can also see that it learns a very interpretable representation of the task space. So every point here in this space is colored by the known target direction that the cheetah had to run in, which was known to the experimenters but not to the agent. And we can see that the learned task embedding that the agent has recovered is very well aligned with our known interpretation of how the task is actually formulated and how the tasks are related to each other. So we can see that the approach that we're proposing here is less prone to overfitting and learns meaningful task embeddings. If you would like to learn more about meta-learning, Shimon will be presenting some follow-up work to this, where we actually look at how agents can learn to rapidly explore in a meta-learning scenario. And he will be giving a talk about this Saturday morning in the deep reinforcement learning workshop. I want to very briefly touch on models. This is typically a very strong kind of set of assumptions that can be used for sample-efficient learning. So I want to touch on those as well. Models are a very good way of introducing structure, and strong results have been observed. If we are in a lucky setting where the MDP is given to us, so we are actually handed the dynamics and the reward structure for the MDP, then we can use dynamic programming for very, very efficient planning. And so very notably, the team led by David Silver at DeepMind was able to show that in that setting, massively scaling up the understanding and results of the past decades on how to make dynamic programming very efficient and use a function approximation to Bootstrap in order to speed it up. Very impressive feats can be achieved. For example, learning to play Go at superhuman level. But what if we're not handed this MDP on a silver platter, but instead we have to learn the model from experience? Can we use that experience to learn a model and then learn to interact with that in that model more effectively than if we were to directly learn, for example, a policy or value function in the model-free setting? The jury is still out on that, but I want to highlight a few examples of recent work where people shed light on this. One key result in this area is based on the so-called PILCO approach by Mark Dyson-Roth and Carl Rasmussen in 2011. In this setting, they addressed a card pull, a kind of balancing task, which you can see on the picture here. So the task is to, from the hanging position, learn to balance this pendulum in the upright position. So it's a control task. And in their work, they show that the model can be parameterized as a Gaussian process, and that in that setting, the model dynamics or the task dynamics can be learned with a very, very small amount of experience, so they can actually learn to control this efficiently in with a couple of seconds of experience. Very recent work in this area is by David Ha and Jürgen Schmidhuber in 2018. This work has generated a lot of interest because it was able to learn models in a high-dimensional visual observation space. They learned a predictive model using recurrent structures and the autoencoder approach. And then they used the learned model to actually learn a policy for how to interact with this. This is really interesting initial work. There are still theoretical challenges that need to be addressed here. So for example, the model might learn errors, and then in that setting, a policy might learn to exploit those errors. So there are key questions around how to systematically update the model in order to avoid overfitting to specific errors that the model makes. A third piece of work that again was published in 2018 was by Chua et al., where they showed how to learn models efficiently, but going beyond maybe some of the computational challenges that are posed by Gaussian processes. Here they showed that they could learn very effective models using ensembles of Bayesian neural networks, and that those ensembles of Bayesian neural networks would appropriately capture the two kinds of uncertainty, aleatoric and epistemic uncertainty, that need to be accounted for in order to plan effectively in a model that might have modeling errors. In their results, they were able to show that they can achieve top performance in, for example, a wide range of Mojoko tasks in a fraction of the number of samples that would be needed by current state-of-the-art model-free reinforcement learning approaches. There's also progress on the theoretical side, and so Wen Sun and his colleagues in 2019 were able to identify and formally describe a setting where they could show that model-based approaches were provably faster or more sample efficient than model-free approaches. Now, this was only for a very specific setting, and the jury is still out on whether, in general, model-free approaches are provably more efficient in a wide range of settings. It's not necessarily clear that it's always the case, so you can imagine that if you have a certain budget of experience of interacting with the environment, learning a model might focus on areas of, for example, accurately modeling transition dynamics in an area that is not even covered or necessary by the optimal policy. So in these settings, it might be actually more sample efficient or faster to directly learn a model-free policy. But as mentioned, there are really interesting questions in this space and a lot of exciting work happening. One final kind of set of work that I want to touch on that was done by collaborators and myself is work led by our PhD student Steindor Simonsen and together with Mark Dyson-Roth. The question here was whether we could use, again, sets of related tasks in order to very sample efficiently learn models so that model-based reinforcement learning approaches could be made even more sample efficient. Again, in this work, we're using the multitask or meta-learning setting that I showed earlier. So we assume that there's a set of related tasks that are related to each other through some low-dimensional embedding. In this example here, you can imagine this as a set of pendulum systems that might be related to each other, but distinct. So for example, each pendulum system might have a different weight of the mass that has to be balanced or different length of the pendulum. So in this setting, we described a set of these tasks. And the approach proposed here was using Gaussian process dynamics, but these were conditioned on a neural network variation autoencoder that kind of explicitly represented this latent variable that showed how the different tasks were related to each other. We were able to show, first of all, that the latent variable embedding that was recovered very much aligned with the task structure that was known to the experimenters, but not to the system. So again, here we can show that the relationship between tasks is learned very effectively. And at the same time, the system was using that information to learn very sample efficiently. So you can see that success rate of the combined approach is going up much, much faster than if we were to learn naively a single policy that covers all those tasks, but without taking into account the structure of how tasks are related to each other. And it also learns much faster than if we were to learn a controller for each task individually. Finally, very recent work out of this collaboration that I'm hugely excited about is looking at how to incorporate even more structure into model-based approaches. The kind of insight here is that we propose a set of variational integrator networks, or VINs, that is able to build in structure from physics. So for example, conservation of energy can be directly built into this. An early result shown here is that if we look at a baseline approach that tries to model a swinging pendulum, with a small amount of data, the previous approach is not able to recover the structure of the problem. But with the proposed approach here, we very kind of automatically get this modeling of the conservation of energy. And so as a result, the model can be learned from only 4 images of, in this case, 28 by 98 high-dimensional visual observations. This work is presented in the Bayesian Deep Reinforcement Learning workshop. So if you would like to learn more about this, I encourage you to check out Stender's poster at the workshop in the 9:35 poster session. Right. I want to briefly conclude with some new challenges that I see that can be used in order to drive progress in reinforcement learning. Over the past couple slides, I showed you some approaches that are looking at how to learn more sample efficiently in a wide range of settings. Here I want to introduce 2 specific types of benchmark tasks that are well set up in order to push reinforcement learning towards sample efficient learning in more and more challenging scenarios. Both of those are based on the Project Malmo platform that I introduced previously. And as mentioned, this platform enables a wide range of experimentation scenarios, 2 of which are illustrated here. The first set of benchmark tasks were introduced for last year's competition on multi-agent reinforcement learning in Malmo. This set of tasks takes the form of 2-player mini-games where agents have to learn to cooperate, coordinate, or compete with each other. There are 3 types of mini-games illustrated here. The mob chase, which illustrates a social dilemma where agents have to collaborate in order to successfully chase a pig or another mob. The treasure hunt, which implements the notion of asymmetric roles, where one agent has to carry a treasure. It's a form of an escort mission, where the second agent is able to defend against zombies and has to ensure that the one carrying the treasure is successfully navigating to the goal. And the third one, a build battle, which illustrates the challenge between trading off individual versus cooperative rewards, where the agents need to collaborate to build or copy a structure. They are rewarded for completing that structure, but at the same time, they get higher rewards for blocks they have placed themselves. Each of those come in a wide range of variants, different appearances, weather conditions, different layouts, and different mobs. And so we think that this kind of set of tasks is a very challenging environment where we can really push reinforcement learning approaches that are able to very quickly generalize or adapt to new variants of tasks. The second benchmark that I want to mention or introduce is the mineral competition on sample-efficient reinforcement learning using human priors. This is a competition that is running at this year's NeurIPS competition track. It's organized by a large number of collaborators from CMU, Preferred Networks, Microsoft Research, Crowd AI, the Queen Mary University, and many others. You see that it takes a village, so there's a very large number of people here. All of these were guided by or led by William Goose, who was the lead organizer of this team. The key question addressed here is how we could push reinforcement learning approaches to really learn a generalizable policy or kind of have a generalizable learning approach that would learn to adapt to a new task within a fixed computational budget. And so this is the first competition that I'm aware of where the participants actually have to submit their agent code. The agent code is then run in the cloud with a controlled budget of data and compute so that they have to demonstrate that their algorithms can actually learn as fast as promised on the packaging. So let's take a slightly closer look at what the competition setup is. So, while you can no longer join this year's competition because results are now known and will be announced in the competition track on Saturday, the benchmark tasks and setup will remain available, and we think that it will give rise to very interesting follow-up work. If you would like to hear about the fantastic insights that our competitors have been able to obtain, I encourage you to check out the competition track on this Saturday. With that, I want to conclude my presentation. This is a very low-tech plot that I made of reinforcement learning related contributions over the past couple of years at NeurIPS. According to my estimate, there are about 209 contributions, so that is estimated by searching for reinforcement in the schedule for this year's NeurIPS. This is dramatic growth over the contributions that were made in previous years. And I'm sure there will be a lot of exciting new insights, huge exciting new material. So I do hope that the current presentation, the current tutorial, give you a good foundation for kind of placing some of the new results that are obtained that you'll learn about over the next coming days. Enjoy the conference.
Hiya, thank you for the talk. I'm at your 11.
Yep.
So I have a question. There's a great focus on transferability of the competence learned by agents, well, which is understandable given the amount of computation needed. But are there tasks for which you can fundamentally say, well, these are uncompatible, and for instance, an agent trained for task A will not perform well on task B and will need to retrain something else from scratch, and this will be cheaper than training agents performing well on A to perform B.
So it's hard to understand questions up here. I'll recap to just see if I understood what you said. So the question is about, there was a lot of focus on generalization, but there are also very valid scenarios where tasks might be not related to each other, where you genuinely have to retrain or update an agent's policy. Does it roughly capture what you're asking about?
Yes, and the question part would be, where do you draw the line? Is it possible to kind of a priori, without having any experience, to say that a couple of tasks are incompatible?
Mm-hmm. Okay, so I think you're asking about how could you learn ahead of time so that the agent can then very quickly adapt to a new task where it does need to relearn certain components.
Or perhaps imagine that whatever happens, we know that we won't be able to retrain the agent.
We won't be able. Maybe we should take this one offline. I'm not sure I understand your question correctly. Sorry for that.
I have a question. Thanks for the great tutorial. So in the context of some of the more sandbox-like environments, I'm curious to hear what you're excited about in the field of intrinsic motivation and task-agnostic exploration, and how those can be applied in that much more open-ended setting.
Yeah, fantastic question, and I think this might be related to the one the previous person was asking. So the question is about how to use, for example, intrinsic motivation in a multitask setting, maybe ones where the reward structure may be not known ahead of time. This is a large area of research. It's one that I didn't have time to go into, but there is definitely a lot of really exciting work, both in the past and currently being done. There is a key question of if maybe an experimenter cannot create an appropriate reward structure for a task or the set of tasks they have in mind, can we create a more generic version of maybe intrinsic reward that would guide an agent towards learning the maybe mechanics of the environment? Over the past few years, there have been a couple of suggestions that propose, for example, notions of intrinsic motivation as exploration bonuses that could, for example, take the form of estimating novelty of a state to some degree, and these kinds of bonuses would draw agents towards exploring the environment and take the form of the reward structure during learning in order to obtain an agent that is able to manipulate its environment. It's a huge and fantastic area, so I encourage you to look out for kind of work at this conference. If you run into any that you find particularly interesting, I'd love to hear more about those.
Thank you.
Hi, your competition made me think about the sample inefficiency in card games like poker because of the non-deterministic and imperfect information. How could this how could these human priors be used to inform better how we understand the distributions and kind of the exponential complexity of the sample space to improve sample efficiency in those types of games. It can be kind of intuitive for a human to think of a rollout in a card game that would have a tree that kind of branches very exponentially, I guess is kind of like the general idea. Yeah.
Thanks for the great question. So the question is about how to use, for example, human priors, data from human demonstrators, for example, in order to make settings such as POMDP settings, for example, like in the game of poker, more computationally tractable. These kind of really interesting results have been shown, for example, in AlphaGo, where initially human demonstration data was used to initialize a policy so that agents would be biased towards exploring a certain part of the state space or of the belief state that would frequently occur under human play. More generally, there are a huge variety of approaches that can be taken. A very obvious one that, again, I didn't have time to touch on would be to start from imitation learning or inverse reinforcement learning to initialize a policy that would roughly mimic what human demonstrators would be doing in those environments. And then depending on how the maybe near optimal human demonstration data could be, this could dramatically reduce the amount of data required for learning. For example, if we were to bias exploration towards covering the space that would typically be encountered by human demonstrators. Again, there's a trade-off for any given application. This may or may not be possible, and it's possible that there are better strategies in a part of the space that humans wouldn't explore, so that would have to be solved empirically.
Thank you. Thank you.
Question here. Do you have any words regarding the relative advantages and disadvantages of DQN versus policy gradients? It seems recently most work is focused on policy gradients. So if you have any examples where like one approach does better than the other, that would be great. Mm-hmm.
Great question. So the question is about the relative advantages of value function-based versus policy gradient-based approaches. I don't think there's any kind of firm consensus on which one is better than the other. The kind of traditional understanding is that value function-based approaches are more sample efficient in settings where they can be effectively applied. And so those are primarily settings where we have small discrete action spaces where the policy can be directly derived from the optimal value or the current value estimates. Directly deriving the policy is much harder in a continuous or high-dimensional action space, and those are the settings where policy gradient or actor-critic-based approaches typically perform better. So I would say both have their pros and cons. In the kind of small discrete action setting, policy gradient or actor-critic approaches tend to be less sample efficient than value function-based approaches, but I don't think that is a conclusive kind of result.
Hi. Thank you for this. This is awesome. One question I had is about some of the work around applying posterior sampling in the MDP setting, which, as you pointed out, can be really difficult. So my question is around, and you touched on it, but I was wondering if you can expand on some of the motivations for why you would want to apply posterior sampling in the MDP setting.
Mm-hmm. So intuitively, posterior sampling can be a very effective approach. So it's based on the principle of maintaining a distribution over environments. So think of a distribution over MDPs. And so if you were able to sample from the distribution effectively and solve for the optimal policy in each of those samples, then you would exactly explore with according to the probability that this MDP is the correct one that actually underlies the environment. And so the intuition for this is very strong. There have been very strong theoretical insights that kind of obtain the same, for example, regret bounds in the Bandit setting. But as mentioned, it's hard to come up with principled approaches that are at the same time computationally tractable that expand this to the sequential setting. Yep.
Yeah, a lot of the breakthroughs and milestones and examples in the reinforcement learning seem to be around games or game environments. I was wondering if there's any other examples, like, say, for instance, acquiring knowledge or natural language tasks or things that aren't like a game kind of environment.
Mm-hmm. Fantastic question, and one area that I wasn't able to touch on was kind of interesting applications of reinforcement learning in natural language processing settings. So something that surprised me over the past years was how rapidly reinforcement learning made its way into, for example, optimizing, let's say, dialogue systems where it might be hard to backpropagate through the entire systems. And so their reinforcement learning is a really good kind of general purpose optimization method that has seen very, very kind of effective uses in those scenarios. Again, for sample efficiency reasons, most of those are settings where there's some kind of proxy simulator that allows learning in this relatively high sample efficiency kind of scenario. When people move towards actual applications of this, they often start within a model or within a simulator and then try to minimize the number of updates that have to be done in the actual target environment. And I think over the next couple of years, we'll see a lot of kind of hybrid scenarios like this. Sim-to-real kind of applications in the robotics setting are another example where we really see those worlds merging closer together and where we see kind of starting in a model, a simulator for very kind of getting the basics right or maybe learning some initial representation with then very, very sample efficient updates once something is deployed in the real setting.
Thank you very much.
Hello?
Last question. Yes.
Hello? So I study reinforcement learning in human setting, and I was really interested in the part when you mentioned there's a lot of human data for the Mineral project. So I wonder if you're aware of any work related to probing the human learning dynamics or anything in that regard. Thanks.
So the question is kind of starting from some of the work I mentioned where there is a large amount of demonstration data for the latest mineral competition related to this. Is there interesting work in understanding human decision making? That there is a huge body of literature, and so a starting point would be in the cognitive science literature. The conference RLDM, or Reinforcement Learning and Decision Making, is an interdisciplinary conference that brings together experts on reinforcement learning that look at the kind of computational, cognitive science, and neuroscience aspects of this field. And so this would be a really good starting point for looking at the literature on kind of what the current understanding understanding is. They're really interesting insights on how humans make decisions and how that often differs from normative approaches that might have been developed on the computational side. And there are also really interesting insights on the neuroscience side, where some of the concepts that we're routinely using on the computational side, like temporal difference errors, seem to have some kind of equivalent in biological learning as well. So it's a huge and really exciting literature. Right. Thank you so much for all your questions, for your attention, and enjoy the rest of the conference.